So is it full screen? Okay. So good evening to all of you. Myself Samaris Ghosh from IIT Roorkee, and we are discussing about different characters and techniques. So the name of this NPTEL course is Characterization of Polymers, Elastomers, and Composite. This is week 11, and the course is 12 weeks course. So we have left only 1 week. So the course already has been taught by Professor Santanu Chattopadhyay, and here myself Samaris Ghosh as a research scholar for clearing your doubt. So just we will recapitulate the previous week uh, characterization, different characterization, and we will see a different case study basically today. So just for your information, we will little bit summarize whatever we have discussed. So last week we have discussed first the optical microscope. Okay, so we know that optical microscope, the anatomy of optical microscope we have discussed. So there is one objective lens, uh, then there is eyepiece, and of course you have an object. So this is objective lens, and this is the object that is placed in between the focal length, and you are observing through the eyepiece. So you are here, your eye is here, and then you are getting the image, a larger image. And we have also discussed different type of microscope, different advancement of microscope, for example confocal microscope, and we have vividly discussed that how you can get a 3D image through the confocal microscope. So basically first you should take the image of the surface and then slice it, and again take the another uh, image of the beneath the surface. In that way you just take 3 4 images, and through software you should create a 3D image of the object. And also another important type of optical microscopy is the phase contrast microscopy. So in phase contrast microscopy there are two extra uh, uh, modification or advancement done, that is annual aperture, and one is the phase plate. So through annulus aperture and phase plate, you will get a phase contrast if you are observing a composite type of material and there are different phase present. So through normal optical microscope, you will not get the variation. So for that, you should go for the phase contrast microscopy. And because of this annulus aperture and phase plate, you will get different intensity of the scattered light, and in that way you will create the image. So here is a case study of a fiber morphology. So you are observing a fiber through a optical microscope, and you are actually observing what are the different features of a fiber. For example, what is the size, and also the cross section, and the orientation of the thread if you go deep or if you magnify it. So this is uh, 1 micrometer scale. Of course, until and unless you are uh, presenting the what is the scale, it does not make any sense basically. So this is 1 micrometer, and this is 1 millimeter. So you see, uh, it, at very high magnification you can visualize the single fabric of a this is a transmitted optical micrograph of a polyester textile fiber, and this is a woven fabric. And if you go up to 1 micrometer scale, you can see a single cylindrical type fibers. And also actually this is there is also presence of different pigment particle on the cylindrical fiber that can you also visualize through the optical microscope. And in case of B, when it is 1 millimeter scale, so it is clearly visible, it is uh, woven type fabric, orlon fiber basically, and there are different protrusion that is observing here. But here there is no as such protrusion is visible, but you can go or you can probe further to see the single thread of the even fiber. The here is also different morphology of fiber and basically the cross section of a fiber, and what are the different shape and size, because you know that shape and size is very much important whenever you are making a composite. For example, you are preparing or if you are developing a rubber based composite and you used filler as a fiber, in that case the size and shape is very much important because that ultimately dictate whatever the mechanical properties and also whatever the adhesion strength, those are very much dependent on the size and shape. So for that, if you want to probe what is the cross sectional uh, uh, the image, if you want to take the cross sectional image of a fiber, so this A, it is showing this circular type of uh, shape, but in case of B, it is showing irregular type, so it has not any particular shape, that is irregular, and you can see the periphery of those uh, fibers basically. The C, that is also another type, that is called the trilobal shape Orion type. Different pedals like morphology are visible. And the fourth one, that is dog bone shape Orlon fiber section. So based on different shape and size, the overall surface area will be different of a fiber. So how much surface area is interacting with your matrix? If you want to probe that, you should go for uh, to investigate the cross-sectional size and shape, you should go for the optical microscopy. Okay. Now third one, this is also another example, that is filler dispersion in a composite. So optical micrographs show the size and shape of several minerals used as filler for composite. So first one is the mica flakes appeared, and the shape you see, that is a plate type of morphology it has, and has irregular boundaries. The second one, that is tack powder. So tack powder, basically what is tack? It is basically silicate type of material, clay material, and they are very fine particles basically. So it has platy structure. The particle exhibit range of different shapes from fibrous. For example, uh, this is the fibrous type, this is plate type. So it exhibit a range of shapes nearly fibrous to platy. And third one, that is clay particle. Those are very finely powdered type of material and without any characteristic shape. Those are the fine powder of clay material. So through optical microscopy, you can check whatever the size of the filler you are using, and the what is the importance why I should go to check the size and shape, because based on the size and shape, the dispersion is very much dependent on the filler size and shape. For example, if it is very much fine powder, so there is much more chance to make the agglomeration when you are dispersing in a matrix. So that's why after dispersion, you can check the composite by making the cross section. You can check whatever the how much agglomeration is there. In that way, you should modify the dispersion technique to get the better result. So this is different. If we have already discussed, so there are different components in optical microscopy. There is eyepiece lens, that is at the top, from where you will look uh, the whatever the uh, material you want to check, and there is objective lens, and you can go to uh, incorporate more than one, three, four objective lens. You can accompany it with your optical microscope to get higher magnification or to visualize more finer material. And there is also condenser lens. The purpose of condenser lens is to focus the light and onto the specimen. Through optical microscope, I can also check the texture of fiber and film. So this one, that is basically a polyethylene fiber cross section, and it is showing the spherulite texture through the polarized microscope, and the fine spherulite structure is observed of the polyester film cross section taken in a polarized microscope. Now, what is the importance of polarized microscope? Polarized microscope, basically you are uh, making the light, polarization of the light through uh, making a specific angle. Now, what is the importance? The importance is, if a material is crystalline in nature, or it has a very high aspect ratio, and for example, if you are using a very high aspect ratio fiber to make a composite, so through polarized light you can check in which direction the fibers are aligned. And another thing, the birefringence technique, that is the difference between the refractive index in parallel and perpendicular to the fiber axis. That means through birefringence, you can check that in which direction, because whenever the fibers are oriented in a specific way, in that direction you will get the higher scattering compared to the perpendicular direction. So one can modulate also the grow of crystals. For example, uh, if you melt a fiber material, so by providing heat, then you are cooling in a slowly. So then the crystal will grow slowly with decreasing the temperature. Now through birefringence, you can modulate, or you can probe that how crystal is growing, because this is the difference between the refractive index. So if in a specific direction the crystal is growing, you will get higher scattering from that direction. So that's why birefringence is very much important. And with this optical microscope, you can get the idea how crystal is growing, or how the fibers or crystalline material are dispersed in a composite. Another important thing, whenever if someone is making a extruded sample, so through the extrusion, how the fibers or other fillers are orienting, that idea you can also get through optical microscope. The another smart, or if the fancy technique is the orientation in presence of electric field. So optical micrograph of polyhexyl isocyanate on a bend device, that is the figure it is given here, and the scale is 20 micrometer. So for that you just make a film on a glass slide, and you should provide an external electric field. Now whenever you are providing an external electric field, how the orientation of your sample is happening because of presence of electric field, that you can visualize through the optical microscope. This is what I have already told you, that if a student film, if you want to check that what is the surface, I mean whatever the wrinkles are forming, or the roughness whatever is appearing on the skin of the extruded film, that can you also check. So optical micrograph of an, this is the image whatever it is given here, that is optical micrograph of an ultra thin longitudinal section of an extruded experimental polyparaphenylene benzobisthioazole PBZ film, and in polarized light with the fiber at 45-degree angle to the crossed polarizer, a definite skin core texture is observed as the skin appears bright yellow and the core appears blue. So this is the uh, yellow color, that is the skin of the extruded film, and this the blue color in between, that is basically the core of the film. Now based on the surface roughness of the skin, of course there must be changes in the property, ultimate mechanical or other property, final properties. So to modulate the extruded condition or different parameter, for example temperature, whatever the speed, that you can verify with the help of the optical microscope. This is another example of a spherulite structure of a molded nylon film. So this is, you can see that the dark and bright images. So polarized light micrograph of a molded nylon cross section. So a non-spherolytic skin that is here, and a rounded isolated spherulite in the transition zone. So a classical Maltese cross extinction pattern is observed. This specific pattern is called the classical Maltese cross extinction pattern, and there is different. You can see the different pedals type of morphology. So by making the contrast, so this is the bright color uh, of the uh, bright. These are the different fibers that present in the matrix. So this black is the matrix, and this white color is the fillers, or the strengthening different inorganic material or fiber, whatever it is. Just by making the phase contrast, you can get at how it is dispersed and how it looks like when it is dispersed in a matrix. Another example of phase contrast optical microscope. So it is a micrograph of an impact modified nylon. So what is the impact modified nylon? Basically, you are uh, you have provided some rubber particles inside the fiber. So in that way, it will absorb the impact. So that's why it is called the impact modified nylon. So the fine dispersion of the modifier in the matrix that you can visualize through the phase contrast optical microscope. So because of this phase contrast, you are getting the bright images, or bright those bright type of particles basically are the uh, rubber type of particle, sorry, nylon, and black is the matrix or rubbery particle. Yeah. And when the fiber has a high crystallinity, that's why it will scatter much more. That's why you are getting a bright type of image. The next is atomic force microscope. So we have already discussed vividly also atomic force microscope, how it works and what we actually measure here. And this is the anatomy of an AFM instrument. So there is a cantilever tip, and we know the tip is usually made of silicon carbide or silicon nitride type of material, very sharp tip and very hard. There is also a laser and mirror, and uh, you are you are visualizing the surface morphology by monitoring the uh, atomic force that is generating when it is the tip is in contact or without contact with the surface. So there are three different way you can take the images. First one is the contact mode. That means throughout the region of interest, your tip is actually touching the surface. In non-contacted mode, that is, it is not touching the surface of your region of interest. And third one, that is in between, that is tapping mode. So it is uh, touching the surface, and in the next it is not touching the surface. And we have also discussed what is the advantage or disadvantage. For example, through contact mode, you will get much more idea from the surface, and through non-contacted mode, you will get the idea about the surface roughness or different phases present in your sample. So much more idea you will get. If you want to get the idea about what are the different phases present, you should go for the non-contact mode. And if someone is interested on the surface mainly, uh, that in that case you can go for the contact mode. But the problem is, in contact mode there is a much more chance to be damaged of that cantilever tip. So this is a potential energy diagram. So whenever it is contact mode, that means it is very much close or it is touching the surface. In that case, the repulsive force in between the atom and the cantilever tip will be high. So that's why it is showing there is the high force whenever it is very close, because of the Coulombic repulsion. And in non-contact mode, it is in between, that is the attraction force is much more dominating here. And in and in whenever it is going in upward direction, or it is the distance is increasing in between the tip and the atom, so obviously the force will very weak. And the governing equation to of the AFM is F equal to minus k into x. And this is the detector. So from left to right and from up and down, you are getting the different force value, and after that you are uh, just by getting the different force value from different direction, and then you make the image through the software. Hmm. So this example is the large scale AFM image of the surface of unstretched thread showing fibers and fibrils in spider silk fiber. So it is in unstretched condition, and whenever you are giving the data, you must also provide what is the height of uh, hi- uh, the height of the cantilever from the surface. So both the scale and the height, both data should be provided whenever you are providing AFM data. And through AFM, I can also get the idea about crystal structure of polymer. So that's why it is very much important, because through optical microscopy it is little difficult, because we know that maximum magnification we can go up to lambda by 2. You see, thus very high magnification, 100 nanometer scale, we are taking the image. And the crystal structure of the polymer, how it looks like, there is a very high crystalline type of uh, uh, polyethylene film with laminar type of structure, and how the laminars are interlocked through the chain stacking, one can visualize it through the AFM. Here it is given the copolymer morphology. So copolymer is one of the important part if I want to investigate basically the block copolymer uh, through AFM. For example, this is a styrene butadiene styrene. It's a triblock type of copolymer is given. So what is uh, the shape, or what is the morphology, whether it is sea island type of morphology or co-continuous type of phase, that we can get the idea through the AFM. So thin film of triplock copolymer, where first you cast it on a silicon substrate. So for AFM, you should prepare a sample, a very dilute sample first you have to prepare. After that, you just cast on a glass substrate or silicon substrate, and then you dry it to uh, evaporate the solvent, and then you should go for the testing. So here it is showing there is styrene and butadiene, two different part. So since styrene, these white colors are because of the polystyrene phase, and the black type of uh, circular shape, those are corresponding to the butadiene part of the copolymer. Another important purpose of AFM is to investigate the adhesion performance, because we know that for adhesion, the surface morphology plays a very important role on the adhesion strength. So intermittent contact mode AFM is also used to follow the changes in the adhesion promoter morphology, to help or to explain the adhesion performance between the polymer dielectric and silicon oxide wafer substrate. So before providing the adhesion promoter, you check the AFM of the surface. So there is a bright color of particle, those are basically dielectric material. And after providing adhesion promoter, how it make the surface smooth, you can get the idea through the AFM. Membrane morphology, to investigate the membrane morphology, one can go for AFM, and for separation purpose, membrane is a part of the separation technique, and the morphology of the membrane also very much influence the separation process. So the image that is given here, it is the structure of a polyamide, basically an affuent membrane, is modified with the graft polymerization of acrylic acid onto the surface to improve the fouling properties of thin film composite membrane, and that is characterized by the AFM. So Nafion membrane is composed of a aromatic piperazine based polyamide layer on top of a polysulfone support reinforced with a polyester non-woven backing. So you see that the bright color is basically the polysulfone part, and the black color, that is basically the semi aromatic piperazine based layer. Now this is very important, that strain induced structural changes. So AFM can very sharply uh, identify if there is any formation of strain, and after strain induction, whatever the morphology is changing. So first one at a 10 micrometer scale, then a second one is at 2.5 micrometer scale, and the third one we further magnify it up to 1.5 micrometer scale. So when it is 10 micrometer, so atomic form microscope phase image showing cross section of a PETG and polystyrene assemblies with different layer thickness. So this is the 60 nanometer, center is 30 nanometer, right is the 80 nanometer. So 60, 30 and 8 nanometer. And you see, whenever there is a strain, that how the polymer chain is orienting. So through AFM you can get the idea, and we know whenever there is a formation, we are straining, we are providing strain on a polystyrene, there is whitening is happening because of the formation of different void, and that's why at the 8 nanometers, the thickness, you can clearly, it is visible that how polystyrene is orienting with the strain. So TPV and TPU, these are also two important field in the polymer. So what is TPU? That is thermoplastic, uh, TPE thermoplastic elastomer, and TPV, that is thermoplastic vulcanized. So it is showing that height left and phase, that is the height image, and this is the phase image. So you should provide both the height image and phase image, then only it will make any sense. Because until and unless you are providing the phase image or height image, I cannot disintegrate it, that from where the uh, I mean whenever the cantilever is tapping, whether it is because of the height, or whether there is presence of different phase, that's why it is proving the force. So are the these shapes are basically this bright type of shape. This is showing the IPP in a EPDM matrix. So how it is also dispersion, and what is the morphology of that part, you can get the idea through AFM. This is another example. This is basically a polyaniline, and you see that how nanotube are agglomerated when you are observing through the AFM. The height sensor is 3 micro scale is 3 micrometer, and the height is minus 4042 to 378, that means around 25 nanometer. So here this bright uh, part is because of the polymer chain. It's not polymer chain, after the agglomerating, how the morphology looks like, that is representing this tube type of morphology. Now surface morphology, if somebody is want to check that after doing the processing, what is changes happening in the surface. So SPM is a very important technique, and that is used in a very broad way to characterize the surface related to the processing. So this is the processing of a BCD dielectric thin film after development and hard thermal cure of the photo-defined material. An oxygen plasma is used to remove the residues in the vial. So these two image, one is after processing, this one is after processing, and this is before processing. Now intermediate content AFM image via holes patterned in a photo BCB film over a copper substrate before plasma treatment to remove the polymer residues, and after treatment. So how the residues removed, so before the treatment and after the treatment, that you can check through the AFM. The next is the electron microscope. So we have discussed that why we should go for the electron microscope, because to uh, further probe in deeper or to magnify in a few lakhs, we must have to go for the electron microscope. And here electron beam is used as a source of illumination, and mainly there are we have discussed SEM, that is scanning electron microscope, and transmission electron microscope, and there are four different uh, technique. So one is the transmitted beam, someone can also analyze the reflecting beam, and scanning beam, and scanning deep, that is STM. Now in SEM, whatever after uh, the primary electron beam is hitting on the substrate, what are the different phenomena that happened, we have already discussed. So there are different uh, type of electron or X-ray generate after hitting the substrate. So first is the secondary electron, and then backscatter electron. So through ACM, mainly these two types of electrons are detected. Others are auger electron, characteristic X-ray, cathode luminescence, diffracted electron or transmitted electron. Those are also generated. So we have already discussed that how secondary electron is generated. So this is the incident electron, and it is knocking out another electron, that is the secondary electron. The next is auger electron. We have also uh, discussed that how auger electron generate. Basically, after knocking out a inertial electron, then to fill up that vacancy, another electron from higher orbital come down. So this is the higher uh, energy electron that come down. So to make the energy balance, another electron will release. So that is the auger electron. That excess energy can also be released by uh, releasing X-ray. So that is continuum X-ray. Then you will get the X-ray, and you can detect that X-ray. Another is the backscattered electron. So these are the different uh, electrons that generate, and we can detect different electron for different electron microscope. In SEM, we mainly uh, detect the secondary electron and backscatter electron. So what is the backscatter electron? That is originated further from the incident beam. The secondary electron escape from the material or from the sample. Those are less tightly bound with the nucleus. We have already discussed that how backscatter electron generate, and auger electron, that is the excess energy that can release another knockout another electron, or that excess energy can release as a X-ray. So we have also discussed that how X-ray is formed. And the next one is the transmitted electron, that is penetrating throughout the sample, and after penetration below the sample you have the detector, and you are detecting that transmitted electron, and that can be used to determine the thickness, the crystallographic orientation, the interface. That is very much important. We discussed that how interface we can analyze through the TEM technique. Different phase present in the sample, because based on the atomic weight, the the transmitted electron will be different. And through ACM, we can check the topography, surface feature of an object. We can also check the morphology, that is, what is the shape and size or arrangement of the particles. And of course, through the EDS, we can also check the composition analysis, what are the different elements present in the compound. So this is different uh, spectra of a TEM, that what are the different thing we can analyze. So first is the bright and dark field image. So that is through getting or through observing, analyzing the bright and dark field image, we can get the idea about internal ultrastructure, nanostructure dispersion, and also the defect identification. Through HRTM, we can probe the interface structure and also defect structure. On top of that, there is also energy dispersive X-ray spectrometry that is already accompanied with the TEM instrument. Through that, we can also check the compositional analysis. The electron energy loss spectroscopy, that can also be combined with the TEM, and with that we can verify the chemical composition or other bonding information. And through electron diffraction, the crystallographic information we can investigate. So TEM as a multi-purpose machine, we both the chemical and physical behavior or physical structure or defects microstructure. So all these we can analyze through the TEM instrument. So this is showing the electron microscope image of a fiber. And it is showing the before and after heat etching, how the surface morphology of a fiber changes. So we know that fiber is a crystalline type of material, and crystalline oligomer particles are shown in the these are the crystalline type of material. So after etching, we know that some part bloom out from the bulk to the surface, and the scale is 5 micrometer. And this is the dark field image, this is the bright field image. You can see that the different roughness you can observe through this bright field image, but it is not that much visible in the dark field image. And this is basically the modulation mode, which it's a different technique that is used whenever you are making the image or taking the image. The next is pre and post processing analysis. So a spray spoon non-woven fabric is shown. So these A and B, this is the secondary image, and after processing, how it looks like. If you see, there are different patches present after processing. So what are the what is the different patches? So because of the crystalline nature, whenever it is undergoing different high temperature processing, their melting of the crystallites can take place. And whenever it is melted, that melted crystalline part are observed here. And you see, if you further magnify it, you can check that how this is creating a higher, and I mean how it can bonded with other fabric because of these crystalline patches that can be visualized. And next part is the application in the tire technology. So this was showing some steel cord, that is RFL modified steel cord. So tire cords by several complementary microscopic method, a cross section of an adhesive coated yarn is shown by optical microscopy. So this is optical microscopic image, that is RFL coated. B is the comparative normal. This is the ACM image, and C and D image show the filmy adhesive coating, and the BAI image shows that the surface has higher atomic number particles on over it. So these are the different these are the presence of different particles on the surface, these small particles. And detailed surface structure that suggests that adhesive is found in higher concentration in the interstitial region between the fibers than the fiber on the surface of this experimental cord. So in between, if you probe further, in between there is much more presence of these particles compared to the surface of the rod. Film and membrane morphology can also be detected. So this is showing a very porous type of film. It is clearly visible. And if someone is uh, comparing that how porosity is generating, so these four images that is given here, the A scanning electron micrograph of several membrane surface reveal the range of pore structure. So there are different pore size. If you compare the size of the pore and this, so of course this is the pore size is different, and uh, the distribution of pore size is also very much important, and that must you can get the idea from the uh, FSM images. So this is microporous polyethylene membrane, and with elongated stretched porous region of various size separated by fibrils. So if you stretch it, that how the pores are the direction or the orientation of these pores, how with stretching, how it is oriented, that can you visualize through the FSM. And why it is important? Because that pore size actually dictate with the efficiency of the separation, because we know that the solvated radius of any ions, depending on the pore size, how it is matching. I mean, whenever a cation or anion has radius in few angstrom or few nanometer, and the pore size, whether it is larger or smaller than the ions, in that way it will influence the efficiency of the separation of a particular membrane. Now, transmission electron microscope in polymer, how they are applied, or whatever different uh, uh, the application of TEM in polymeric sample. So globular structure that is difficult to evaluate using scattering technique because of the poor electron density. So we know if the material is not electrically conducting, so the intensity of the scattered electron will be low. So that's why you need TM. And in case of FSM, we know that you must have to first coat the material with a electrically conducting substrate. That's why you need gold coating. Until and unless it is electrically conducting, you will not get any image through SEM. So those compound, those are poor electrically conducting. TM is very much important. So after the deformation in presence of heat and surface heating or chemical attack, strain induced contrast enhancement, that is showing here, that plastically deformed polystyrene at a high voltage TM, that how it looks like after deforming the polystyrene film. This is the SAN polymer, that is styrene acrylonitrile polymer, and craze like of deformation zone ahead of crack tip in a SAN copolymer in a and at larger magnification, that is 100 nanometer, and this is 0.5 micrometer. Now this white color part is because of the styrene, and this is for the acrylonitrile. Now you see that very high electron volt is required, around 1000 kilovolt. That's why it is high voltage transmission electron microscope. And whenever there is a formation, crack is taking place, the how crack is propagating, if you want to check, or after cracking, if you want to investigate that from where the crack is generating, that idea you can get from the tape. That is compatibilization study. So influence of a compatibilizer on the morphology of a polyamide and polystyrene blend at a different ratio. So this is the polystyrene part. So it is 2 micrometer. When you are increasing the compatibilizer, how this is dispersed or distributed in your matrix, that you can easily check through the TEM analysis. And one important thing is the selectively stained with ultra-thin section. So sometimes there are different staining agent actually used to get the idea how they are uh, in a very large matrix, how they are dispersed. For a specific uh, chemical, there are different specific staining agent that actually required, and that process is also very much complex. How you should stain a specific sample. This is a rubber modified polymer. This high impact polystyrene with resin. So this is the resin. This is the resin, and this is the polystyrene. So this is zero 0.5 micrometer, 1 micrometer, and zero 0.2 micrometer. Now how this the periphery of the acrylonitrile and butadiene styrene, you can get the idea that what are the different size and how the phase boundary, it is the phase boundary that you can check through the TEM. Next is the fiber modified composite or nanocomposite. So if you want to check that how failure takes place after failure, if you check the cross section, you see both are 10 micrometer. So it is showing that the fiber can be easily taken taken out because it is not well interacted or well bonded with the matrix. But here this is the fiber, it is very strongly bonded with the matrix, but here it is not that much strongly bonded. So obviously by checking the cross section of the fractured sample surface, you can modify the further uh, to get the better strength or better property. Epoxy based clay nanocomposite. So you can go up to 50 nanometer. So that is the beauty of a TEM. That much magnification can be possible. And change of the basal spacing of organoclay. So this is much more uh, agglomerated than during the processing of epoxy resin and clay nanocomposite by the sonication technique. Now T image of the nanoclay in different epoxy systems showing intercalated white arrows or exfoliated black arrows. So that means uh, since clay is a layered type of material, how the polymer is intercalated in between the layers of the clay, that can you identify through the PEM. If you check these two images, so this is showing the clay material and this is showing that polymer is very efficiently intercalated. That's why the despacing that has already increased here. So through this you can also check the exfoliate the how much exfoliation is already done after mixing or after sonicating the uh, fillers or clay with the resin type of material, because until and unless the polymeric chains are intercalated in between the layers, you will not get the better property from the composite. So we have already discussed that how you should prepare a sample for FESEM. So since uh, it is electrical beam is we are detecting the secondary electron or backscatter electron, so it must be electrically conducting. That's why this is the sputtering technique. So gold plate is kept here, and after creating a very high vacuum and providing a very high voltage, that gold nanoparticle will be spattered on the surface. So here you will put your sample and then make the sputtering to make the surface electrically conducting. This is the TEM and HRTM. So HRTM is high resolution TEM. So resolution below couple of nanometer, you can check the uh, to get the 50s. For example, this is 15 nanometer. It is high resolution TEM, and you can clearly visible the internal between the two phase, that is CO2 and silicon. But here that is standard TEM, so it is not that much clear the phase boundary. So this is internal layer. It is silicon surface. This is CO2O. This is the interface. Now through HRTM, you can much more get deeper knowledge about the interface, because the electron beam is much more intense and you will get high resoluted image. Now the problem in TEM is the sample preparation is complex, uh, and also you need a TEM grid, that is also costly. Now polymers, since they are organic substance particularly sensitive to electron beam irradiation, that is also a problem little bit. And the contrast between the structural detail is often very low, because polymers usually uh, organic com organic part, so that's why only carbon, hydrogen, oxygen, these are the main elements that present in polymeric material. And because of the lighter nature of this atom or elements, they will interact very weakly with the incident electron beam. So if you have any doubts, please ask me. Otherwise, there are very 3 4 question. Before that, if you want to ask something, or if you have any doubts, I can clear. Anybody has any doubt that how you can analyze a FSM image or TEM image or FM image? Okay. So first is polarized light is unidirectional, bidirectional, multidirectional, or none of the above. What is the polarized light? We have discussed in polarized microscope. Yes, polarized means it is unidirectional. The next is which one of the following statement is or are correct. So first is secondary electron imaging corresponds to the topography. The next is EDS, spectral dispersive systems. Next, current in the surface. What are the two emission takes place? There are different electron or electron, secondary electron, secondary electron, and also there are two type of collision, elastic collision and inelastic collision. Based on that, whatever the nature of the collision, you will get different electron. So I am repeating once again that secondary electron imaging corresponds to the topography. Energy dispersive X-ray provides data about phase difference. It is correct. Let's see. So EDS provides data about phase difference, but actually uh, it is incorrect. Why it is incorrect? Now, energy dispersive X-ray ds, we will get the elemental composition. It's not phase difference. We'll get what are the different elements because it is the inherent property of an element from which element the electron is releasing. Just based on that, the X-ray will be energy of the X-ray will be different based on the element to element. So you will get the idea about different elements. For example, if there is presence of zinc and nickel, you will get that idea from ADS. But for the different phase present, that you cannot get. Now choose the increasing order of resolution of the following. So we have discussed electron microscopy, optical microscopy, and atomic force microscopy. Based on that, you tell me that which is the increasing order of resolution. The first is the list is the optical microscope, then AFM, then TEM, then HRTM. The second option is the least resolution is optical. After that, HRTM means high resolution tape. Then AFM, then TEM. Second is wrong. Third one, optical, same, FSM, AFM. It is also wrong. Then optical, AFM, HRTM, and TEM. So A is the correct answer because optical microscope we can maximum go up to 200 nanometer because we know that 400 nanometer is the least. So 400 by 2 that is 200, up to 200 we can go. Then AFM, then TEM, then HRTM. So right answer is the option A. Now match the following: the electropolicing, ultramicrotomy, efficient and scanning probe. And the column is field emission gun, polymers, biological sample, HTM and metal. So electropolicing, ultramicrotomy, efficient scanning probe. Okay. FSM is field emission gun. Yes, right. C3 is A, right? So in between C and D, which one will be the right one? Uh, so think what we sir, little bit think that why I should go for the electropolicing. Electropolicing is required for what? To make electropolicing is required to make it electrically conducting, right? So metals are electrically conducting. Electropolicing, sir, electropolicing, that means you are making the substrate electrically conducting, right? Electrically conducting. Now, if you check that IB and ID, so for D, since it is metal, it is obviously it is electrically conducting. I don't need to make it electrically conducting. Now you got na? So option is ID, uh, and then 2 is ultramicrotomy is B. Yes, for yes, yes. So this is the most correct one. This is the most correct one. So, sir, uh, today up to this, and if you have no doubts, so I will close. Yes, 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 sure, sure, sir. Okay, okay. Thank you.